Now, I introduce the problem of statistical inference. What is the problem of statistical inference? In real life situations, we are asked to make certain statements, we are asked to verify the certain claims. For example, the government wants to know the expected growth rate of the economy, and for example, there will be more exports, there will be less, what will be the size of the GDP and so on. We want to know what would be the total agricultural production in the country in the next year. We want to know what is the infant mortality rate in a particular geographical region or in a particular state. We want to know what would be the reaction of the population to a certain constitution amendment which the government wants to make. We want to know whether a particular diet program is helpful in reducing to the weight for certain class of people. We want to know whether a certain new medicine will be more effective in curing a certain disease. In all of these statements, we are concerned about certain numerical measurements or attributes. For example, in the problem of finding out the effectiveness of a certain medicine, we may like to know that if the medicine is given to a target group of patients, then whether more patients get cured because of this compared to a previously used medicine or not. That means, whether the proportion has increased. Here the attribute is whether the person gets cured or not. Whereas, if we are looking at say mortality rate, then we may be interested in the number. For example, if in a particular year or in a particular month these many children are born, then per thousand of children how many children survive after say 1 month or after 1 year or after 5 years. We may look at the average age of a population. For example, in India we say that the average age or average longevity of a male is 63 years, or average longevity of the general population is 62 years, or we say in Japan the average longevity is 77 years. So, all of these statements are concerned about certain thing called numerical measurements, which we call population. So, population is a collection of numerical values regarding the characteristic in which we are interested. Now, in order to say something about the population, for example, if we want to say something about average, we want to say something about variability, we want to say something about range, then one thing is to have the complete enumeration, but complete enumeration is not possible in most of the practical cases, and therefore, one takes a subset of the population which we call sample, and this sample is then ordinarily called, or we use the notation x 1, x 2, x n, which will correspond to the values of the random variables which are there in the sample. Now, when we make the assumption that it is a random sample, that means each unit of the population is having the same probability of getting in the sample, then for the population whatever distribution is there, we have the same distribution for each of the observations here. So, we say each of this is having a probability distribution, say p theta, theta belonging to theta. Now, when we say p theta, here theta denotes the parameter of the population. So, in general the parameter of the population is unknown. For example, when we say normal mu sigma square. So, normal mu sigma square has two parameters, mu and sigma square. If I say Poisson lambda distribution, then lambda is the parameter of the population or the distribution. So, in general the problem of inference relates to make a certain statement about the unknown parameter of the population. Now, this statement could be of several forms. One is to give a value for that parameter. For example, we want to know what is the arrival rate in a service queue at a railway reservation counter. So, we want to know what is the value of lambda. So, this is called the problem of point estimation. or problem of estimation. In place of one value, if we want to give an interval of the values, for example, we may say that the number of persons arriving between 8 a.m. to 10 a.m. is anything between 100 to 120, then it is an interval. Then that is called the problem of interval estimation. If we want to check, that means we have taken a sample of the patients whom a new drug has been given, and we want to know whether the new drug is more effective, that means more number of people get cured or not. In that case, we are checking a statement, because previously we know the proportion of the people getting cured, probably the previously it was the number was say half. Now, we want to know whether more than 50% of the people get cured, then we want to test something. This is called the problem of testing of hypothesis. Now, I will concentrate on the problem of point estimation. So, our model is that we have a random sample, let x 1, x 2, x n be a random sample. So, that means they are independent and identically distributed random variables, independent and identically distributed random variables from a population with distribution. I use a general notation p theta, where theta belongs to theta. This theta could be scalar or vector here. Now, based on we want to estimate a parametric function say g theta. Now, for estimating we have to make use of the sample, that means we will assign a function of x 1, x 2, x n, which we call a statistic. Any function of the observations is called a statistic, and we are using it to estimate. So, we call it a point estimator or an estimator of g theta. Now, let us start with a very simple example. Suppose we want to estimate average heights of the adult males in a given population. So, what we say when we are considering the population, that population could be maybe say they are from normal distribution. That means, the adult heights if are denoted by random variable x, it may follow a normal distribution with mean mu and variance sigma square. We want to estimate mu. Now, we have taken a random sample x 1, x 2, x n from this population. Now, one may suggest that use x bar, which is actually one of the functions of the random sample. One may suggest that x bar can be used to estimate mu. Okay? But some other person may say that x bar may have certain disadvantage. For example, it is affected by the extreme values. So, one may say use x median, that is median of x 1, x 2, x n for estimating mu. One may say use, for example, geometric mean of x 1, x 2, x n and so on. One may propose various values. Similarly, if we are considering estimation of sigma square, I may consider variance term calculated from the sample, that is 1 by n sigma x I minus x bar whole square. Earlier I have also used the notation 1 by n minus 1 sigma x I minus x bar whole square, which we called sample variance. So, one may suggest using this. One may use say mean deviation from the median or mean deviation from the mean. Once again the question arises which one should be used. So, that brings us to certain criteria of estimation. So, there are various criteria of estimation. We will consider here only two of them. One is unbiasedness. So, an estimator T x is said to be unbiased for g theta if expectation of T x is equal to g theta for all theta. Physically, if we want to interpret this statement, it means that on the average T x must be equal to g theta. That means, if I consider all possible samples and then if I take the average of the T x value calculated from the all the samples, then it should be equal to g theta. Let us consider examples here. Suppose I have an observation from binomial distribution. That means, this is the number of successes conducted in n trials here, n is of course known here. The problem is of estimating p, where p lies between 0 to 1. Then one may consider, say, expectation of x by n, then naturally this is equal to 1 by n into expectation of x, that is n p, that is equal to p. So, you can say here that the sample proportion x by n, sample proportion is unbiased for population proportion, which is unknown to us. Let us take another case, say x 1, x 2, x n following Poisson distribution. Then we may define, say, T 1 is equal to, say, x 1. Let me define, say, T 2. T 2 is equal to, say, x 1 plus x 2 by 2. Let me define T n, that is equal to, say, x 1 plus x 2 plus x n by n. Let me also define, say, s square, that is 1 by n minus 1 sigma x I minus x bar whole square. Let us check. Expectation of T 1 is lambda. What is expectation of T 2? That will be lambda plus lambda by 2, that is equal to lambda. If I consider expectation of T n, that is also lambda. If I consider expectation of s square, then that is also equal to lambda. So, we have several unbiased estimators. So, T 1, T 2, T n, s square, these are all unbiased for lambda. Of course, then we will introduce some other criteria to check which one is preferable among these. We introduce the concept of minimum variance unbiased estimation. So, we say T is minimum variance unbiased estimator, we say V m v u e. So, we say uniformly, because over the whole parameter space it should be u m v u e of, say, g theta if T is unbiased and if T 1 is also unbiased, then variance of T is less than or equal to variance of T 1 for all theta. So, there are methods for deriving the unbiased estimators. For example, there are methods of minimum variance unbiased estimators. For example, there are method of lower bounds. There is a method using the completeness and sufficiency of the statistics, etc. However, we will not get too much into detail here. I will end up with two more applications of the unbiasedness here. Let us consider, say, x 1, x 2, x n following normal mu sigma square. Then expectation of x bar is mu and expectation of s square is sigma square. So, unbiased estimators of mu and sigma square exist here. Suppose I want to calculate for, say, mu square. Suppose my g function is mu square. Okay. Now, then let us look at this. X bar follows normal mu sigma square by n. So, expectation of x bar square is equal to mu square plus sigma square by n, and this we can write as mu square plus expectation of s square by n. This you bring to the left hand side. So, you get expectation of x bar square minus s square by n, that is equal to mu square. So, x bar square minus s square by n is unbiased for mu square. In fact, one can show that this is UMBUE, but that will require some additional arguments. Let us take x 1, x 2, x n following normal, say uniform 0 theta distribution. If I consider x bar, then expectation of x bar is equal to theta by 2. So, 2 x bar is unbiased for theta. We have another concept that is called consistency of estimators. So, T n, that is equal to T of x 1, x 2, x n. So, we are showing exact dependence that there are n observations taken. So, I am writing here T n. This is consistent for g theta if expectation if probability that modulus T n minus g theta greater than epsilon goes to 0 as n tends to infinity for every epsilon greater than 0. Let us take the case of unbiased estimation. I have considered several examples. I will take each of these here. Let us consider say binomial NP here. X follows binomial NP. Let us consider probability of modulus x by n minus p greater than epsilon. We can use Chebyshev's inequality here, then this is less than or equal to variance of x by n divided by epsilon square, that is equal to 1 by n square epsilon square into variance of x. Variance of x in the binomial distribution is n p q divided by n square epsilon square. Now, in the denominator I have n square here. So, this goes to 0 as n tends to infinity. So, x by n is consistent for p. Let us take the second example x 1, x 2, x n following Poisson lambda. Here I have introduced several estimators. T 1, T 2, T n etcetera. Let us take for example T n, then T n minus lambda greater than epsilon. Once again it is less than or equal to variance of T n by epsilon square, that is equal to lambda by n epsilon square. So, this goes to 0 as n tends to infinity. So, T n is consistent for p. However, if I consider T 1, then that is equal to probability of modulus x 1 minus lambda greater than epsilon. Now, this does not depend upon n. So, this cannot go to 0 as n tends to infinity. So, T 1 is not consistent. I will end this criteria unbiasedness and consistency by stating two results. If the mean exists, then the sample mean is unbiased. Sample mean is unbiased for the population mean. So, if the population mean exists, that means if expectation of x is defined, for example, in the case of Cauchy distribution expectation x is does not exist. So, in that case this statement will not be true. If the population mean exists, then the sample mean is unbiased for the population mean. If the population variance exists, then the sample mean is consistent for the population mean. This statement I am saying because of using the Chebyshev's inequality in the previous two examples, because here variance is being used, in this case also variance is being used. However, if you use the weak law of large numbers etcetera, then we may not also require this condition, and we can say only that the sample mean is always consistent for the population mean. That means, sample mean must exist. Now, we discuss certain methods for finding out the estimators. Methods for finding estimators. The finding out of unbiased estimators or consistent estimators is relatively easy, because we can guess about the function here, but there can be other cases. For example, I may consider a log normal distribution, I may consider a uniform distribution with 2 parameters, I may consider exponential distribution with 2 parameters. So, in these cases it is not so easy to guess the form of the unbiased estimator or the consistent estimator. So, in that case, firstly let us have a proper method for deriving the estimator, and then we can proceed to check their desirable properties. So, one of the first, or you can say elementary methods, is the method of moments. Let theta be k dimensional parameter and consider mu 1 prime, that is expectation x, that is the first moment. So, it will be some function of theta 1 theta 2 theta k, mu 2 prime, that is expectation of x square, that is equal to say g 2 of theta, and so on. Consider kth moment, that is say g k of theta. Suppose we can solve, let us call it system 1. Suppose we can solve the system 1 as theta 1 is equal to say h 1 of mu 1 prime, mu 2 prime, mu k prime, and so on. Theta k is equal to h k of mu 1 prime, mu 2 prime, mu k prime. Let us define sample moments, say alpha 1 is equal to 1 by n sigma x I is equal to 1 to n, alpha 2 is equal to 1 by n sigma x I square I is equal to 1 to n, and so on. Alpha k is equal to 1 by n sigma x I to the power k I is equal to 1 to n. In method of moments, we replace mu I prime by alpha I for I is equal to 1 to k in system 2. That is theta 1 method of moments estimator, let me call it theta 1 head, that is equal to h 1 of alpha 1 alpha 2 alpha k, and so on. Theta k head is equal to h k of alpha 1 alpha 2 alpha k. Now, this is the general guideline. If I have a 2 dimensional parameter, then I will consider in general 2 moments, but sometimes we may have to take 3 also, or sometimes we may have to take only 1, because there may be interrelationship between those parameters. So, but this is a general guideline that if I have a k dimensional parameter, then I will consider k moments. Let me explain through the examples here. The method of moments estimators may or may not be unbiased. They will be consistent if the inverse functions h1, h2, hk are continuous. Let us consider the Poisson lambda case. Then here mu 1 prime is equal to lambda. So, lambda head method of moments estimator is equal to simply alpha 1, that is equal to x bar. So, if we see here our several proposed estimators for the lambda in the Poisson distribution case, the T 1, T 2, T 3 and T n and s square etcetera. Among them x bar is the one which is obtained through the method of moments, and here x bar is unbiased as well as consistent. Let us consider say x 1, x 2, x n following uniform 0 theta. Here the first moment is theta by 2, and therefore, we get theta head method of moments estimator as 2 mu 1 prime. So, mu 1 prime will be replaced by alpha 1, that is x bar. So, that is 2 x bar, and once again this is unbiased and consistent. Let us consider say x 1, x 2, x n following normal mu sigma square. Here mu 1 prime is equal to mu and mu 2 prime is equal to mu square plus sigma square. So, when we write the solution, mu is equal to mu 1 prime and sigma square is equal to mu 2 prime minus mu 1 prime square. So, the method of moments estimators for mu it will be x bar, and for sigma it will be equal to 1 by n sigma x I square minus x bar square, that is 1 by n sigma x I minus x bar square. Here if you look at expectation of x bar, that is mu, but expectation of sigma head square that is equal to, because 1 by n minus 1 is unbiased. So, 1 by n will be expectation of 1 by n sigma x I minus x bar square, that is equal to n minus 1 by n expectation of s square, that is n minus 1 by n sigma square. So, sigma head square is not unbiased. However, it will be consistent. For sigma square. Let us consider say suppose combined weights of passengers and their luggage in kilograms are uniformly distributed on the interval a to b. The weights observed for a random sample of 8 passengers are 90, 135, 120, 127, 115, 108, 96, 112. We want to find out the method of moments estimators for A and B. Now, if I assume say x1, x2, xn following uniform A to B, then mu 1 prime is equal to A plus B by 2 and mu 2 prime is equal to A square plus B square plus A B by 3. So, if we solve for A and B, here I will get A is equal to mu 1 prime minus square root 3 mu 2 prime minus mu 1 prime square, and B is equal to mu 1 prime plus square root 3 mu 2 prime minus mu 1 prime square. So, A head will be equal to x bar minus square root thrice 1 by n sigma x I minus x bar square, and B head will be equal to x bar plus square root 3 by n sigma x I minus x bar whole square. So, if I consider this particular sample here, then x bar in this problem turns out to be 112.875 and this value 1 by n sigma x I minus x bar whole square, that value turns out to be 14.0396. Therefore, A head turns out to be 88.56 and B head turns out to be 137.19. So, the method of moments estimators for A and B are 88.56 and 137.19. Another more popularly used and more powerful method of estimation or for finding the estimators is called the method of maximum likelihood. In method of maximum likelihood, so I will use the word MLE or maximum likelihood estimation or maximum likelihood estimators. We consider the probability mass function or probability density function f x theta and write for x 1, x 2, x n. So, this will become equal to f of x I theta product I is equal to 1 to n, and we denote it to be likelihood function, and I will change the nomenclature from f x x I theta to f L theta x, where x is denoting the sample values here x 1, x 2, x n. This is called the likelihood function of theta. What does it mean? Suppose I am considering probability mass function, then f x I theta in case of discrete PMF, you will have f x I as probability of x is equal to x I when theta is the true value of the parameter. Okay. So, when we consider product of f x I theta, we can write it as probability of x is equal to x 1, x 2, x n is equal to x small x to small x 1. That means, this is the probability of observing the sample x 1, x 2, x n when theta is the true parameter. In method of maximum likelihood, we interpret it in a different way. We call it the likelihood of the sample when theta is the true parameter value, and we maximize this L theta x, this L theta x as a function of theta. Naturally, when you maximize over theta, you have to consider all values of the parameter over the parameter space here, where you may have theta belonging to a parameter space theta. We maximize L theta x with respect to theta. Say the maximum occurs at theta head ml, that is equal to theta head ml x1 x2 xn. That is, you will have L theta head ml is greater than or equal to L theta x for all theta belonging to theta. Then we say that theta head ml is the maximum likelihood estimator of theta. Let me explain through certain examples here. Let us consider binomial NP where n is known. Here the probability mass function NCX p to the power x 1 minus p to the power n minus x, where x can take values 0, 1 to n and p lies between 0 to 1. Then we are considering this as now the likelihood function. So, I will call it as a function of this. Now, we want to maximize L p with respect to p. Now, p is ranging over an interval. So, we can apply the usual methods of the calculus, like we can try to see that whether L is an increasing function or decreasing function, or the range where it is increasing and then where it is decreasing, etc. We can simplify the situation by looking at equivalently we may maximize log of L. So, we use a different notation, log likelihood. So, this is called log likelihood. So, LP here turns out to be log of NCX plus x log of P plus n minus x log of 1 minus P. Let us consider the derivative of log likelihood with respect to P. So, here x is not a variable here, we are considering it as a function of P, that is why I am not putting x here, that is equal to x by P minus n minus x divided by 1 minus P, that is equal to x minus n p divided by p into 1 minus p. Now, note here that this is equal to 0 actually if x is equal to if p is equal to x by n. Okay. So, this is certainly greater than 0 if p is less than x by n, it is less than 0 if p is greater than x by n. So, if you plot the L function, on this side we have p and on this side you have L p, then starting from 0 onwards, the value of this as p goes to x by n, this is increasing, and when p is greater than x by n, this is decreasing. Naturally, the maximum is occurring at x by n. So, the maximum occurs at p is equal to x by n. So, P hat ML, the maximum likelihood estimator for the population proportion or the probability of success in a binomial distribution turns out to be x by n. Now, notice here that here P was in the interval 0 to 1 and you can see this x by n also lies between 0 to 1. There may be a situation where we have some prior information about this parameter P. For example, we may know that suppose it is related to certain success failure experiment, where we may know that say P is less than or equal to half or P is greater than or equal to half. In that case, we will not write the answer x by n, because x by n then may cross the region. In the method of maximum likelihood estimation, we have to consider the maximization over the given parameter space only. So, let us consider that analysis here. Suppose it is known that say P is less than or equal to half in this problem. If P is less than or equal to half, let us consider there are two possibilities then. See, we had this as x by n, on this side you have P, this is LP. If P is less than or equal to half given to us, then there may be two cases. Case 1, x by n is less than or equal to half, that means P is somewhere here, P is equal to half is somewhere here. In that case, the maximization occurs at x by n, but there may be another case that P by n is P is equal to half is here. In that case, if you see, this x by n goes out of the region of the parameter. Therefore, we cannot consider x by n as the maximum likelihood estimator. You notice the likelihood function in the region 0 to half itself. Now, in this region the maximum value is attained at half. So, in this case, when x by n is say greater than half, then P hat ML you have to take to be half. So, the answer is P hat ML, it is equal to x by n, that is, it is equal to minimum of x by n and half. So, you can see here that there is a direct effect of the parameter space on the maximization problem or the optimization problem, as we may call it. Let us take some more problem. Say x 1, x 2, x n follows say uniform distribution on the interval 0 to theta, where theta is of course greater than 0. Now, in this case the likelihood function, this is equal to the joint density function. Now, in the case of uniform distribution, the density is 1 by theta over the region that each x I is between 0 to theta, it is equal to 0 elsewhere. Now, if you look at this thing directly and try to maximize with respect to theta, then you will get an absurd result, because this is theta in the denominator. So, theta should go to 0, but that will give us the value as infinite. So, this will give an absurdity here, and of course, when you are considering the parameter space from 0 to infinity, then saying that theta is equal to 0, which is not dependent upon the observations, is an absurd result. So, where we are missing is that we are ignoring the region. So, if we look at the region properly, we can write this likelihood function in a more appropriate fashion as 1 by theta to the power n, indicator function of the set. So, firstly let me say, we can write it as, if I consider the order statistics, that is x 1 is equal to minimum of x 1, x 2, x n, x 2 as the second minimum of x 1, x 2, x n, and so on, x n is equal to the maximum of x 1, x 2, x n. These are known as x1, x2, xn are called order statistics of x1, x2, xn. So, we can write the region as now you see from here, if I am looking at 1 by theta to the power n, the minimum value of theta that is possible is x n. So, theta hat ml is equal to the largest order statistics. You compare it with the method of moments estimator for uniform distribution. The method of moments estimator for the uniform distribution was two x bar. So, here the two things are quite different, and we may also consider whether it is unbiased or not. For example, we may consider the distribution of x n, that is n x to the power n minus 1 divided by theta to the power n. So, if we consider expectation of x n, that is equal to integral n x to the power n by theta to the power n dx 0 to theta, that is equal to n by n plus 1 theta. So, x n is not unbiased for theta. However, it remains consistent. And we may also consider alternatively like T 1 is equal to n plus 1 by n x n, then expectation of T 1 will be equal to theta. So, from the maximum likelihood estimator we can consider little bit of adjustment to make it unbiased. In fact, it can be shown that this is minimum variance unbiased estimator of theta. Let us consider x 1, x 2, x n, a random sample from say normal mu sigma square distribution. This is a 2 parameter problem. So, here the likelihood function will depend upon mu and sigma square, that is the joint density of x 1, x 2, x n, that is equal to product I is equal to 1 to n 1 by sigma root 2 pi e to the power minus 1 by 2 x minus mu by sigma x I minus mu by sigma square. So, that is equal to 1 by sigma to the power n root 2 pi to the power n e to the power minus 1 by 2 sigma square sigma x I minus mu square I is equal to 1 to n. So, log likelihood function, which I denote by small l, it is equal to minus n by 2 log sigma square minus n by 2 log 2 pi minus sigma x I minus mu square by 2 sigma square. If we consider say del L by del mu, I get sigma x I minus mu by sigma square, and this is nothing but n times x bar minus mu by sigma square. So, easily we can see it is less than 0 if mu is less than x bar, it is greater less than 0 if mu is greater than x bar. So, as a function of mu, if you see, it is increasing up to x bar and decreasing up after x bar. Therefore, the maximum likelihood estimator of mu will become equal to x bar. On the other hand, if I want to consider with respect to sigma square, then I differentiate with respect to sigma square, I get minus n by 2 sigma square plus sigma x I minus mu square by 2 sigma to the power 4, which we can consider as 1 by 2 sigma to the power 4 sigma x I minus mu square minus n sigma square. Once again you notice that this is greater than 0 if sigma square is less than 1 by n sigma x I minus mu square, and it is less than 0 if sigma square is greater than 1 by n sigma x I minus mu square. Therefore, the maximization of sigma square occurs at 1 by n sigma x I minus mu square. but this involves mu which is unknown, but maximization with respect to mu we have already considered, that is obtained at x bar. So, sigma head square m l, that turns out to be 1 by n sigma x I minus x bar square. In this particular case, these estimators are same as the method of moments estimators for this problem, and naturally here x bar is unbiased for mu, but 1 by n sigma x I minus x bar whole square is not unbiased. We have certain remarks here regarding the maximum likelihood estimators. Under certain regularity conditions, maximum likelihood estimators always exist and they are consistent. In fact, they are strongly consistent. Under these conditions, the asymptotic distribution of MLE under these regularity conditions is normal. So, this maximum likelihood estimators are quite useful. In general, they are dependent upon the sufficient statistics. I have not introduced the concept of sufficient statistics in this course till now. They are strongly consistent, they always exist under regularity conditions, and the asymptotic distribution is normal. So, these are all large sample properties which are satisfied by the maximum likelihood estimators, and that is why they are quite preferred in statistical theory. Of course, there are certain situations where one can find better estimators than maximum likelihood estimators also, but by far these are most commonly used. I will just end this lecture by introducing the concept of better. So, we can define the concept of mean squared criteria, mean squared error criteria. So, for estimating a parametric function say g theta, we may have estimators say T 1 and T 2. Then we say that T 1 is better than T 2 if expectation of T 1 minus g theta whole square is less than or equal to expectation of T 2 minus g theta whole square for all theta. This term, this is called the mean squared error estimate of the estimator T 1. This is called the mean squared error of the estimator T 2. Let us consider the estimators T 1 and T 2 in the Poisson example. T 1 was x 1 and T 2 was x 1 plus x 2 by 2, where x 1, x 2, x n were Poisson lambda, and also we had considered T n as equal to x bar. Now, consider here mean squared error of T 1, that one is lambda, mean squared error of T 2, that will be equal to lambda by 2. If I consider mean squared error of T n, that will be equal to lambda by n. So, certainly T n is better than T 1 and T 2. There are general concepts of loss functions. In place of this squared error, one may consider some other loss functions such as absolute error, power 4, Linux loss function, log squared error or entropy losses. That general concept of loss gives rise to expression known as risk function, and then one prefers the estimator which has the smaller risk function. This topic comes under the general concept of decision theory. So, we do not intend to cover in this particular course. In this particular course, we will also consider interval estimation and testing of hypothesis. So, I will plan to cover it in the following lectures here.